Okay, today we're going to talk about energy. We have three big ideas to go over when we talk about energy. We're going to talk about the two main types of energy and how you can calculate them. So that means we'll get two new equations today. We're also going to talk about some subtypes of energy. So within those two big types, what are some other common types of energy? And then lastly, we're going to talk about something called the law of conservation of energy. First, we need to know what energy is. Energy is the ability to do work or to cause a change. Lots of different things have energy. Sound has energy, motion has energy. There can be energy from being above the ground due to gravity. There can be energy in electricity. All of those types of energy would provide the ability to do something, the ability to cause a change. Most energy can be classified into two general categories. So here are our big categories. Most energy can either be classified as potential energy. This is one kind. The symbol for potential energy is capital P, capital E. Potential energy is energy that is stored in something. It's like the potential to do something, or it could be the energy of a position. If an object has a very high position above the earth, then I kind of like to think about how that object has a very large potential to fall. So it has a lot of potential energy that way. So it's energy that's stored or energy of position, the potential to cause a change. Another example is an archer who is just about to shoot an arrow. When you pull the string back, there is energy stored in that string because the string is stretched to its capacity. As soon as you let that string go, then that energy is being used to make a change. So while the string is pulled back, it's potential energy. It has the potential to cause a change. Another example would be the top of a roller coaster. So when the car is right up here at the top, this car has a lot of potential energy. It has a large potential to fall down to the bottom of the coaster. The equation for potential energy is potential energy equals m times g times h. And two of those three things we know already. We should know what M stands for. We should know what G stands for, and you might be able to even guess what H stands for. The M, of course, is mass. Mass still needs to be measured or labeled in kilograms. The G is the acceleration due to gravity, and we learned in our last unit that that number is 9.8 meters per second squared. And the H, you might be able to guess that the H stands for height, and height will be measured in meters. So if you're looking for potential energy, you take mass times gravity times height. The second major kind of energy is called kinetic energy. Remember, most energy can be classified as either potential or kinetic. Kinetic energy, the symbol is capital K, capital E, and that is called the energy of motion. Anything that's in motion has kinetic energy. So as an example, the arrow that has now been released and is flying towards its target has kinetic energy. Another example would be the coaster on the way down. Once it's in motion, then it has kinetic energy. And here's our new equation for kinetic energy. Kinetic energy is equal to 1/2 times mass times velocity squared. So to do this equation, you're going to have to learn a couple of things. How do you put 1/2 into your calculator? If you have a fraction button, you can use it. Otherwise, remember that 1/2 is 0.5 as a decimal. You might want to put a little note, maybe above 0.5, remember 1/2 is 0.5. And then the other thing that you're going to have to learn on your calculator is where your squared button is. Usually it says X with a little 2 on the top. something that looks like this maybe. It depends on what calculator you have. You're gonna have to look at your calculator and figure out where your squared key is. Other pieces to this equation include m, which of course still stands for mass. Mass is measured in kilograms. And the v, we should already know, that stands for velocity, which is measured in meters per second. If we're going to be calculating the numbers for potential energy and kinetic energy, we need to know what our label or what our unit is for energy. Energy has a new label. We haven't learned this one yet, so this one is new. And that label is called joules. The symbol for joules is a capital J. It is named after this scientist, James Prescott Joule. He lived from 1818 to 1889, and he's famous for doing a few things with chemistry as well. You'll come back in a couple years and you'll learn some of those things. But for now, we need to know that his last name is the label for energy. In this country, when we talk about food and energy, we talk about calories. If you travel to Europe or Australia, they actually use this unit of energy on their food labels. So instead of seeing things in calories, you see things in joules. Okay, that was our first big idea. Every type of energy can pretty much be classified as either kinetic or potential. Now we're going to take some more specific kinds of energy and do a little description and a couple examples of each one. So the first one we're going to talk about is mechanical energy. Mechanical energy just means something that's not electrical, something that actually has moving parts, something that's not sound, it's not a magnet, it's not any of those other kinds of energy. Mechanical energy can be both kinetic and potential. It depends on the situation. And it's the energy that's associated with motion and position of everyday things. Mechanical energy would be like the pistons in your car's engine going up and down, things that actually move or change position. Couple other examples, a train traveling down the tracks has mechanical energy. So does a ball that bounces off the floor, or athletes as they run down the track. The next type of energy that we need to know is called thermal or heat energy. We're going to come back and talk about this quite a bit, a little bit later in the year when we do some chemistry stuff. What we need to know right now is that thermal energy is kinetic energy, and that is because this is the energy of the motion of particles. Think like atoms and molecules. Atoms and molecules are always constantly in motion, and that motion or that energy is kinetic energy, and it's also thermal energy. The faster the molecules are moving, the more heat that they produce, the more thermal energy or kinetic energy they have. An example of something that puts out thermal energy or heat energy would be just something as simple as a candle or an electric space heater that maybe you use to keep your feet warm in the winter. Next kind, chemical energy. Again, we're going to come back and talk about this quite a bit later in the year. What we need to know right now is that chemical energy is potential energy, because this is the energy that is stored in chemical bonds or in compounds. When you have two or more atoms that are bonded together, that bond stores a certain amount of energy, and that's potential energy. If you happen to break bonds and pull those atoms apart from each other, then your potential energy goes up. Again, we're going to come back and talk about this a little bit later in the year when we talk about chemistry. A couple of examples though, simple examples. The gasoline that you put in your car has energy in its bonds, and when you break those bonds, when you burn the gasoline, then that changes that energy and gives it to your car. Food is another example. For humans and animals, when you eat food, there's a certain amount of energy in those chemicals, in the bonds, in the food, and then your body breaks down the food and you get that energy out. This is also how batteries work. A battery has a certain amount of stored chemical energy, and then when you put it into an electronics device, then that battery gives that energy to the device and makes it run. Next kind, radiant energy. This is kinetic energy. Radiant energy is the energy of electromagnetic waves, including light. So this is the kind of energy that we get from the sun. This is the kind of energy that you get from a microwave or a radio wave. And this is something that we'll talk about quite a bit in a couple of months when we come back and talk about sound and light and the waves and different types of energy that are associated with it. And again, here's some of those examples. Solar energy from the sun, X-rays, like if you break a bone or they're checking to see if you've broken a bone, and radio waves. Next one, sound energy. Again, we're going to talk about this in a couple months too. This PowerPoint's turned into a little preview of where we're headed this year. Sound energy is kinetic energy, and it is the energy that moves through substances through compression waves. We're going to talk about what compression waves are in a couple of months. The sound energy has to move through a substance, through the air, through the water, through the ground. And as those molecules move, they transfer the sound one to another. Examples, of course, would be when you hear music, when you hear a pencil hit the floor, when you hear my voice talking to you through the PowerPoint. Anything that makes a sound has sound energy. And electrical energy. You're probably pretty familiar with this one. This is kinetic energy as well, molecules in motion. It's the movement of electrical charges. Movement of electrical charges. You might know that batteries have a positive end and a negative end. The movement of those charges or electrons from one end to the other is what provides the electrical energy. And examples, of course, electricity in the wires like in your house or in our school, and then lightning is another interesting example of electrical energy. And the earth science classes are actually talking about that right now. One more, nuclear energy. This one you don't talk about quite as much. It's a little bit less common. We do have one nuclear power plant in the area that I know of in Cordova. Nuclear energy in general is potential. It has the potential to cause a change because it is the energy that is stored in the nucleus of an atom, and it holds the protons and the neutrons together. Examples of how we use nuclear energy or where you find it. Nuclear energy is what powers the sun. That's the process of fusion where atoms come together to make bigger atoms. And of course, power plants, which is the opposite process of fission, where we're splitting atoms and getting the energy released from that process. Okay, third big idea is called the law of conservation of energy. Conservation generally means to save something. So this is the law of saving energy. Energy is going to be saved or conserved. There's a few parts to this law. The first part says that energy may change forms, but it cannot be created or destroyed. A lot of times I will compare energy to money. Money is not supposed to be created, at least not by you, and it's not supposed to be destroyed by you either, but it can change forms. You could have dollar bills, you could have coins, and it can also change where it's going, from person to person, from you to the store, from you to the bank, etc. So energy is a lot like money. It can change forms, it can move around, but it's not supposed to be created and it can't be destroyed. Second part of this law says that if energy is conserved, then the change in potential energy is equal to the change in kinetic energy. This is a new symbol for you. This is a Greek letter. It's called a delta. It looks like a little triangle right here and right here. That little triangle means change in, the change in potential energy. However much potential energy is lost, that much kinetic energy has to be gained. Energy has to be conserved, it has to go somewhere, or it has to change forms. We're going to spend some time looking specifically at the conservation of mechanical energy. Again, that's the energy of motion or energy of position. So, for example, if we had like a roller coaster and we had a certain amount of energy at the beginning, that amount of energy would be the same as what we had at the end. So whatever kinetic energy and potential energy we have to start with, we have to end the roller coaster with that same amount of kinetic and that same amount of potential energy. Or at least I should say the total of those two things together should be the same as the total of these two things together. We can't lose energy. Energy has to be conserved. You could draw an energy flow chart to show how the energy changes form, and that could simply just be some symbols like kinetic and then an arrow to potential. And we'll show some examples of that a little bit later on in the slideshow. Okay, so here's one example of the law of conservation of energy. Think about a rubber band. The life of Stretchy the rubber band. If you stretch the rubber band out, there's motion involved. You're stretching the rubber band. That's kinetic energy. Well, when you stretch it all the way to its end point, almost gonna break but not quite, that motion stops. And all that energy is changed into potential. And if you think about that, that probably makes sense because you can feel the energy in the rubber band wanting to pull itself back to its original shape. All of that energy that started as kinetic, the motion of you pulling the rubber band, is changed into the potential of that rubber band to snap back to place. If you then release the rubber band, all of that potential goes back into kinetic because all of that potential energy when it was stretched goes into making it snap back into place, and as it snaps into place, it moves. So then that becomes kinetic. Notice before we do the last one here, this is a very simple energy flow chart. Kinetic changed into potential. Not much of a chart, but it gets the idea across. This is an energy flow chart. Kinetic changes to potential, potential changes to kinetic. If, however, you were to break your rubber band, or whatever potential energy it had is released as heat and sound. There is some heat given off when you break a rubber band, although you probably can't feel it with your fingers. You could, however, hear the sound. And that sound is the energy that's being released from that rubber band. Okay, we've been through our 3 big ideas for today. Let's go through a few example problems so you can see what we actually have to do with this information. Here's the first one. It goes with this picture. And the question says, what is the potential energy at points A through E? So there are several questions to answer here. The first one says, you have a ball at the bottom on the ground, and then you have a sphere up here on top, on a wall maybe it looks like. What is the potential energy at point A? Well, on top of the wall, it's the same height as on top of this triangle. Here's point A on top of the triangle. And if it's got 30 joules of potential energy on top of the wall, and that's the same height as point A, then point A would also be 30 joules. These two things are at the same height. They have the same potential energy. We're assuming here that it's the same sphere or the same ball. Remember that potential energy is equal to mass times gravity times height. So if it's the same ball, it has the same mass. Gravity is always the same. And if it's at the same height, then those 3 things together have to make it have the same potential energy. Next one is point B. Again, point B is at the same height as point A. So the potential energy at point B would be 30. And before we do C and D, let's go ahead and skip down to E. Because you can see when the ball is on the ground, its height, when it's on the ground, would be 0 because it's not above the ground. And if the height is 0, what happens to your equation? If the height is 0, then it doesn't even really matter what mass and gravity are, because anything times 0 is 0. So potential energy anywhere on the ground is going to be 0. 0 joules at point E. And now we got to figure out what's the potential energy in between. What's the potential energy at C and D? This one's a little bit harder, but if you look at the steps are approximately a third up. So if we've got 0 on the bottom and 30 on the top, what could we count by to give us equal divisions? Remember, it looks like the steps are divided into thirds. If you're thinking this one should be 10 and this one should be 20, you would be correct. And I just know that because there's 3 steps. They're all placed evenly. The top is 30 and the bottom is 0. Next question. To demonstrate a cheerleading stunt, Agatha has to lift Jenny over her head to a height of 2 meters. Jenny has a mass of 50 kilograms. What is Jenny's potential energy? When I'm doing these problems, I like to make myself a list. Potential energy is what I'm looking for. We'll make this a little thicker here. Potential energy is what I'm looking for. I know the height. Height is 2 meters. I also know the mass. The mass is 50 kilograms. The last thing that I know is gravity, because unless we went to the moon, gravity is always the same. My equation says potential energy is equal to mass times gravity times height. So that means my potential energy is 50 times 9.8 times 2. You could do that on your calculator and you would end up with 980, and the label for that is joules. 980 joules. Next example. What is Jenny's kinetic energy while she's held above the ground? Question. Kinetic energy is energy of motion. If she's being held above the ground, is she moving? No. So Jenny's kinetic energy, if she's not moving, has to be 0. We don't need to do any math for this. She's not moving. And if she's not moving, her kinetic energy is 0. Next question. Agatha gets tired, oh no, and drops Jenny from the 2-meter height. What is her kinetic energy just before she hits the ground, and how do you know? Well, you might think, okay, kinetic energy is equal to kinetic energy is equal to 1/2 mv squared. And you might be thinking, all right, I know Jenny's mass from before was 50, but what's her velocity? Doesn't say anything about that in the question. So there must be another way I can solve this. And it has to do with that third big idea that we talked about. The law of conservation of energy says that energy can't be lost. So whatever potential energy Jenny starts with at the top has to be equal to the amount of kinetic energy that she has at the bottom. Because remember, if she's on the ground, she doesn't have any potential. But she's moving just that split second right before she hits the ground. So whatever potential she has at the top has to be equal to the kinetic that she has at the bottom. And you might remember from 2 questions ago, the amount of potential energy at the top, which is equal to the kinetic energy at the bottom, we calculated earlier was 980 joules. I know these equations are going to take some practice. That's why you have a practice worksheet. Please see me if you have questions.